Hello, welcome back to Cardinal Science. Today we're looking at the Edexcel IGCSE Chemistry specification for 2017. Specifically, specification points 1.10 describe these experimental techniques for the separation of mixtures, simple distillation, fractional distillation, filtration, crystallization, and paper chromatography. In addition, we'll also be looking at point 1.11, understand how a chromatogram provides information about the composition of a mixture, point 1.12, understand how to use the calculation of RF values to identify the components of a mixture, and 1.13, practical, investigate paper chromatography using inks and food colorings. Stick around to the end of the video and we'll talk about how these will be examined. Specification point 1.10 describes separation techniques. There are 5 of these, and for each one you have to know what it's used for with regard to what it can separate. So, before we go on, we have to clarify that we understand 2 other terms, soluble and insoluble. A solute that is soluble dissolves in a particular solvent, and one that is insoluble doesn't dissolve in a particular solvent. So, for example, and we'll refer to this most of the time with regard to water, we say something being soluble, i.e. it dissolves in water, or insoluble, it doesn't dissolve in water. Of the 5 that we have to study, we'll start with simple distillation, and we use this to separate 2 liquids with different boiling points. If we have a mixture of more than 2 liquids with different boiling points, then we'll use something called fractional distillation. If we want to separate an insoluble solid and a liquid, then we'll use filtration. If we want to separate a soluble solid and a liquid, then we'll use crystallization. And if we have more than one soluble solid in a solution, then we'll use paper chromatography. Simple distillation, used to separate 2 liquids with different boiling points. So how can we separate a mixture of water and ethanol? Well, water has a boiling point of 100 degrees C and ethanol of 78 degrees C. So if you have a mixture of these 2 in a beaker, just like in the diagram, how could we figure out how to separate them? Well, if you use a setup like I've got in the diagram, a Bunsen burner with a tripod, we have our beaker containing the mixture and a thermometer. What would happen if we heated up the mixture towards 78 degrees? Well, as the temperature of the mixture reached 78 degrees, the ethanol will begin to boil, and therefore turn into a vapour and escape from the beaker. However, the water within the mixture would not boil. The water doesn't boil until 100 degrees C. So as long as we kept the temperature of the mixture between 78 degrees C and 100 degrees C, we would boil off only the ethanol and therefore leave the water behind. We would therefore have effectively separated the ethanol and the water. However, the problem with that setup is that the ethanol vapour would be lost. If you wanted to keep it, you would use a setup like this. This is the typical simple distillation setup. You heat your water and ethanol mixture, and the ethanol turns into a vapour. It then travels down this tube. Now this tube has around it a condenser which has cold water going in one side and out the other. This cold water causes the ethanol vapour to cool down, falling below its boiling temperature, and it therefore condenses back into a liquid, continues travelling down the tube and falls into the other beaker. If you were to continue heating the water-ethanol mixture, as long as you kept the temperature between 78 and 100 degrees, you would end up with ethanol in one beaker and water in the other, and the mixture would have been effectively separated. Fractional distillation is a very similar procedure. However, this time you've got more than 2 solvents within your mixture. You're going to have to be careful about how you monitor the temperature throughout this experiment. If you're heating up your mixture from room temperature, then when you hit 65 degrees, the methanol inside the mixture is going to boil on its own. It will therefore leave the mixture, move into the condenser, it will condense in there and come out in the beaker on the right hand side. Once the temperature begins to get close to 78 degrees, we will move this away and replace it with a separate beaker. At 78 degrees C, the ethanol would start to boil, and it would turn into a vapour, it would move into the condenser, it would condense, and it would dribble down into the fresh beaker that we have there, therefore leaving the water on its own in the original mixture container. So what we've managed to achieve with fractional distillation, therefore, is taking a water, ethanol and methanol mixture and separating them out into 3 separate beakers containing pure water, pure ethanol and pure methanol. Filtration. We use this to separate insoluble solids from liquid. So if you've ever used a net, a colander or a sieve, you've been doing filtration. Now in science we use filter paper to do this. In this example we have a mixture of water, some floating green stuff and some purple stones. And we want to separate those insoluble solids from the liquid. So we pour the mixture into a funnel that contains filter paper. The water will move through the small holes in the filter paper, but the insoluble solids cannot, so they will therefore remain in the filter paper. Thus, we've effectively removed the solids from the liquid and separated them. Crystallization. We use this to separate soluble solids from liquids. So for example, you might have a sugar solution or a salt solution if you're doing it at home. Or at school you might have an experiment where you have a copper sulfate solution here. The key principle behind crystallization is that when a solvent within a solution begins to boil, it will evaporate, leaving the solute behind. Therefore, if you boil away the solvent completely, you'll be left behind crystals of the solutes that were dissolved within it. So, to achieve this, we put our solution in the setup as you can see on the left here, with a Bunsen, with a tripod above it, a beaker containing water, a crucible or an evaporating dish, and your solution will be in there. We'll then heat the solution until it's reduced by about half, at which point we'll leave it to dry naturally on a windowsill or somewhere warm. As the solvent evaporates, the crystals of the dissolved solutes will begin to form in the crucible. Therefore, we've effectively separated the solvent, which in most cases is water, from the solutes within it. So you might get your sugar crystals back, your salt crystals back, or you might see some nice copper sulfate crystals in blue forming in your evaporating dish or crucible. Paper chromatography, used to separate more than one soluble solid. On the left here we have a chromatography setup. We have a beaker with a small amount of water in the bottom. We have a piece of chromatography paper with a line in pencil drawn along it, and 3 blobs of ink or dyes put along that line. Now the water will be absorbed into the chromatography paper, and as it moves up the paper, the constituent parts of each of those dyes will be separated out, as you can see on the right. What's very important about paper chromatography is that this technique can show us what is actually within each mixture. So we can see from this chromatogram here that ink A contains a red dye and a yellow dye, that ink B contains a blue dye and a yellow dye, and ink C contains a red dye, a blue dye, and a yellow dye. Furthermore, the position of each of those dyes is also characteristic of the dye itself. So, for example, the fact that these 3 yellow dyes are all in a row, they've all moved the same distance during the experiment, means that they are in fact the same yellow dye. Likewise, the blue dye and the red dye, having both moved the same distances, are also the same dyes. We therefore know that ink C contains the red dye from ink A, the blue dye from ink B, and the yellow dye from ink A. This is very important and is used in forensic science. Aside from just looking at 2 spots, seeing that they've moved the same distance and therefore assuming that they're the same dye, we can also do this quantitatively. But first, there are a few things we need to clarify. The original line drawn in pencil on the chromatography paper, we call that the baseline. That's where the inks began. The line now at the top that I've drawn up there is called the solvent front. This is where the water has moved up to in the course of the experiment. We need to be comfortable with where these 2 things are if we're going to move on to calculate the RF values. To calculate the RF value, we need to divide the distance that the spot has moved by the distance that the solvent front has moved. So the first thing to do is to measure the distance between the baseline and the solvent front. In this case, it's a 10 centimeter distance. So all of our calculations right now will be the distance that the spots moved divided by 10. So for number 1, we need to measure from the middle of the spot, and we'll do this for all the spots. So as long as we measure the same position in each spot, this is okay. You can see that it's moved 9 centimeters. Therefore, we do 9 divided by 10 and get an RF value of 0.9. For spot number 2, we can see it's moved 6 centimeters. Therefore, it will be 6 divided by 10, and it will have the RF value of 0.6. Spot number 3 has moved 3 centimeters. and therefore it will have an RF value of 0.3. Spot 4 has moved 4 centimeters, has an RF value of 0.4, and spot 5 has moved 7 centimeters and therefore has an RF value of 0.7. Now we've calculated our RF values, we can put them to use. As you can see, there are 3 red spots on this diagram. However, we can show unequivocally that since they have different RF values, they can't be the same dye. There must be 3 different red dyes. This is very important. However, if you look at the 3 yellow dyes at the top, number 1 and the 2 blank dyes, you can see that since they're all yellow and they're all at the same position with the same RF value, they would therefore be the same dye. This allows you to figure out what the constituents of an unknown mixture are, because you can look at the position of the spot, calculate the RF value. If you find spots with the same RF value within the unknown and the known, you can therefore identify the unknown inks. For specification point 1.13, you need to carry out a practical. You need to do paper chromatography yourself. To do this, you'll need some chromatography paper, a bowl or a beaker, water, food colouring or felt tip pens. You'll draw a line along the bottom of the chromatography paper. You'll fill the water into the beaker so it's below the line. You'll do a few dabs of felt tip pen or food colouring along that line, and you'll allow the water to be sucked up into the chromatography paper. You'll notice in this diagram that I haven't shown anything holding the chromatography paper at the top. You would of course need something above or to the side of the beaker to hold it up. Okay, so we've covered the content. Now let's consider how it's examined. For specification point 1.10, it's common that students are asked to suggest a separation technique for a given mixture. For example, which separation technique would you use to separate the following? Mud mixed with water, where you'd use filtration. A solution of salt and sugar, so that's 2 soluble solutes within a solution, so you're thinking paper chromatography. Ethanol mixed with water, simple distillation. Copper sulfate dissolved in water would be crystallization, and crude oil, which is a mixture of many different solvents, you would use fractional distillation. For each one of these, you would need to describe how to carry out the separation method, as described in the previous slides. Okay, for paper chromatography, there are some very common and very frequently used exam questions. You might be given a chromatogram like this and be asked to say what is present within a specific mixture. So you might need to therefore say that ink A contains a red dye and a yellow dye, and B a blue and a yellow, and C a red, a blue and a yellow. Furthermore, a very common question is to ask you to calculate RF values, compare them and decide whether dyes are the same, as we did previously, by figuring out the difference between the baseline and the solvent front, and calculating the RF values by dividing the distance each spot moved by the distance that the solvent has moved. So in this case, for spot 2 and spot 3, we can see that they are not the same dye because they have different RF values. Spot 5 is at 0.7 and therefore is not the same as these of the other two either. Now for 1.13, the practical element of this is a very common exam question. Okay, they ask you about the different reasons for making certain choices within the experimental setup. What they might do, for example, is to draw an experimental procedure and ask you what's wrong with it. Almost always, one of the mistakes that they make is by drawing that baseline in pen. If you draw a baseline in pen, the ink within the pen will run into the experiment and ruin it. Okay. The second mistake that you should always notice, and in any of these questions you'll find, is that the water level must be below the samples. Otherwise they'll dissolve in the water before the experiment begins. This works both with you being asked to describe or draw the chromatography setup, as well as commenting on a setup given by the examiners. Thank you for watching. Don't forget to hit the like and subscribe button if you found this video helpful, and keep an eye out for future videos.